Okay, sorry, it took a little bit of time to log into here and get started. Anybody have any questions before we start? Anything? Okay. Just a reminder, obviously the final projects are due Tuesday. And again, I'll send an announcement just to kind of remind everyone, best is if you send me PowerPoint or PDF or whatever it will be of slides, and we'll put them on this computer so that we don't have connection transition things. But if you absolutely have to, for some reason, use your own laptop, I highly recommend coming like the night before or something, or the afternoon before when there's not a class, and checking your connection, make sure you know how to connect it here, so that we can go quickly through everyone's presentations. We only have about 5 minutes per presentation, so it's going to be kind of rapid order. Okay, so there's no questions. I'll pick back up where I left off last time. So it's the last lecture that I'm giving to this semester. So I thought what I'd do is cover all of machine learning in one lecture. That's obviously partly a joke. But as I mentioned last time, these concepts from information theory, entropy, and Kullback-Leibler divergence sort of permeate throughout all of modern machine learning, at least I would argue. And so let's come back to what we had ended on, the KL Divergence definition. We'll see how far I get into the description of all of machine learning in one lecture. I have no more lectures to bleed into next time, so I just will have to stop where I get to. I think I can pretty much at least get everything I want to get in, maybe not all the details, but at least a high level of everything I want to get in to talk about. So what we did last time, we defined KL divergence, which sometimes see written as DKL, sometimes just written as KL. But reminder that it is a measure of discrepancy between two probability distributions, kind of on the same set of possible values here. P and Q are two probability either densities for continuous random variables, or their probability mass functions if they're discrete, a discrete random variable. Excuse me. And the definition we had was that this is the expected value over the Q distribution of the log of the ratio between the P density or mass divided by the Q density or mass. This definition, again, doesn't care if you're discrete or continuous, but just to write it out in the continuous case, I'll kind of probably be writing everything in continuous values. Oh, sorry, maybe I've got this backwards. The should be over the P distribution, the expectation. We will kind of switch P and Q around in a little bit later, so it's important to keep track which letter we're doing where. But the first distribution is what we're taking the expectation over. And the first distribution appears in the numerator. The second distribution here that you're putting in the KL divergence is in the denominator. That's the only place it shows up in the equation. Okay, so let's say, yeah, we've got a continuous random variable. We'll do the expectation over the P distribution. So you have an integral of P times the inside of the brackets that we're taking the thing we're taking the expected value of. So that's where we get the log P of X divided by Q of X. Obviously, integral over X. Okay. Right. So that's what we had seen last time. just as a side note, I think I did this last time, you can obviously break the log into log p minus log q. If I take the division and make it subtraction after a log, right? This whole thing looks like the expected value of log p. Again, this is over the p distribution. Let's see, yeah, minus expected value over the p distribution of log q. Oops, log q. Okay. And this thing with the minus sign is what we call cross entropy between p and q. And this thing, remember, it's just the definition we had of the very basic Shannon's, Claude Shannon's definition of what we call entropy for just the p random variable. So this is the entropy of p with a negation for the expected action minus log. Okay. So one way to think of the KL divergence is that you're looking at the cross entropy if, and think of cross entropy is if I'm sampling from the p distribution. Okay, what is my expected value of log q? Okay, so and remember, log q we said is a measurement of surprisal or information. So one way to talk about cross entropy is that if I am sampling a random variable p, what is the surprisal if I'm kind of measuring it as if it were a log distribution? Okay. So that's one way to think of this term, this cross entropy term. And another reminder, this is where we have the universal theory of everything, that this is everything in machine learning. This cross entropy term is what you typically, almost all classifiers in machine learning have at the end of the day, a cross entropy loss. I mean, not necessarily always, but almost always, a classifier will use cross entropy. And there, the P is your true labels, and those are hard labels, right there. You know the exact values with 100% certainty. This is a cat, this is a dog, this is a horse, this is a cow, what have you. And so these are, if it's a binary, let's say it's a binary classification, these are like 0 or 1. The probability is just exactly 0 or exactly 1. Let's say for just dog or cat. And then the Qs are the outputs of your classifier. The probability, it's going to be a continuous number, probability between 0 and 1 if it's a dog or a cat, okay? And the cross entropy, the expected value is, of course, a sum over your batch, which, in the limit, you're really trying to take a sum over the entire data set, the expected value of the entire data set. You're minimizing this cross entropy. So that's where we see cross entropy usually in machine learning, but here in the KL divergence, we see it shows up again as this second piece of the story. So yeah, so you have this cross entropy, which we says the amount of surprisal you have if you think you're coming from the Q distribution, but you're really sampling from the P distribution. Okay. And then you subtract from that the total amount of entropy from the P distribution, and that gives you, in the end, the KL divergence. Okay. So yeah, so what we're going to do in this last hour is look at how the KL divergence, as I mentioned before, I asked where have we seen this before, and the answers were, we've seen this in variational autoencoders, we've seen the KL divergence in diffusion models, and I'll throw one more out there. The KL divergence comes up, if you remember Amon's lecture, of the unsupervised learning, where we did clustering, and we had Gaussian mixture models where I'm trying to cluster my data into different Gaussian distributions, that each Gaussian distribution represents a different cluster. The KL divergence came up there in the expectation maximization algorithm. The EM algorithm is how we solve that type of problem. So really, you've got classification, unsupervised learning, generative models, all of this information theory, entropy, cross entropy, KL divergence shows up throughout all of it. So I'd like to say this is the most important lecture of the semester, save for the last week. It kind of ties everything together that we've talked about, although there's no geometry. I mean, obviously all those methods we talked about where geometry comes up, but this is all probability that we're doing here. And of course, when we do VAEs, for instance, and diffusion models, there are manifolds underlying the data distribution. And we'll see if I get to the end, we'll see the Q is kind of has within it, we already saw this in the VAE, but I'll kind of remind you, I guess I should say, the Q is what we used as an encoder, a probabilistic encoder in the VAE. And so that is where you get this kind of immersion of a manifold through autoencoders, but it all ties into, again, this probabilistic setting with KL divergence and so forth. Okay, so before we get to that, let's just do a little bit of mathematics to understand what exactly is going on with the KL divergence, get a better feel for what it does. So let's look at some properties of KL divergence. So number one, the KL divergence is not symmetric. So if you say the divergence between P and Q, that's not the same thing as computing the divergence. I mean, in general, I should say, it's not the same as computing divergence between Q and P, flipping the order. This is very important. We will look at what's the difference if I flip the order to get a sense of what's going on here in just a minute. Okay, but that's the idea. So notice, yeah, this is why we call it a divergence, the divergence, and not distance. Because remember, distance has to be positive and or greater than equal to 0. It has to also be symmetric, and it has to satisfy the triangle inequality. KL divergence does not satisfy triangle inequality either, but so it fails to be a distance. So you can't say that KL divergence is the distance between two probability distributions. Technically, it's not a distance. You can make it a distance. There is a thing called Jensen. You can, I should say, use it as an ingredient in a distance called the Jensen-Shannon distance. And it's a little bit weird. I would call it JSD. The tricky part is JSD. Sometimes people mean Jensen-Shannon divergence, and sometimes they mean Jensen-Shannon distance. So you have to be a little bit careful. But I will say the divergence version is just to symmetrize the KL divergence. So you take the KL divergence from P to the average P plus Q over 2. And you average that with the KL divergence from Q to P plus Q over 2, the average density. Okay. And I'm not sure, sometimes, I mean, I'm not sure actually if you put it in one, I think you put the 1/2 at the outside also. But you can leave, it's just a constant, but it makes it a nice average of two things. So this is the Jensen-Shannon divergence, and then the Jensen-Shannon distance, to make this a distance. So obviously this is now symmetric. I switch P and Q and I get JS divergence is the same. So now, but it still doesn't satisfy the triangle inequality, but it does turn out to be, this actually turns out to be a square distance. You can prove that it's a square distance. So to make it I should put P and Q in here. To make it a distance between P and Q, you just have to take a square root of the Jensen-Shannon divergence. Okay, so KL divergence in and of itself is not a distance, but if you symmetrize it and square root it, you then get a distance. So if you need a distance between two probability distributions, this is a useful thing to do. But for the things that we've talked about, like VAEs, the EM algorithm and mixture models, the diffusion models, and so forth, we don't actually care about distances per se. We actually only care about the things in KL divergence that are important to us, which are that it is still a measure of how different P and Q are. And if you minimize KL divergence between P and Q become the same. If you could move one of these distributions to minimize KL divergence, then you would be making them equal, which is the next property. That's the key property we need in machine learning, and we use KL divergence, is that KL divergence between P and Q is greater than or equal to 0. So it's always non-negative. And the key part of that is that the equality only happens when P and Q are the same up to measure 0 sets, meaning this is an if and only if P is the same as Q, what's called almost everywhere. If you're familiar with measure theory, you know the phrase the phrase almost everywhere. And that basically means that if you have two, it really makes more sense for continuous things. Like if I had two densities, P and Q, they overlap, they're exactly the same, but you could have like a single point where you just have a difference. Let's say this is Q's value is different, but it's probability distributions, it doesn't matter because you integrate. And so having a difference at a point which has probability 0 doesn't matter. So almost everywhere means only in probability 0 places would you maybe have a discrepancy between P and Q, and that doesn't matter as terms of definitions of probability distributions. That's a very hand-wavy idea of almost everywhere. Okay, so this is the key property that we really utilize when we use KL divergence in variational methods and the EM algorithm, because in all of these machine learning problems, what we're trying to do is we're trying to model a data distribution. Let's call P the data distribution, but we have no idea what that distribution is. And so we have to model it with a simplified model of a probability that we can work with, and that's kind of a Q. So we try to get the Q as close as possible to the data distribution. And what the KL divergence tells us is if you could minimize KL divergence, your model to your data distribution, bringing it down is a good thing. You can't go negative. It's always positive. So the more you can bring it down, if you get it to exactly 0, then you've perfectly modeled your data distribution. Okay, so that's kind of the intuition for why KL divergence is a nice thing. This property right here. Okay. Any questions up to this point? We're going to kind of go through where we've seen KL divergence. It's kind of like a rehash of some things, but it'll be now that we understand a little bit more about KL divergence. First, I'm going to prove this property, so I'll start there because this is kind of the key, cornerstone of machine learning, if you will. So we don't do many proofs and derivations in class, but this is a key one. So I'll do this proof, but then we'll see, once we understand this property, again, rehash where we've seen it before. It kind of, again, ties together multiple things from machine learning all into one kind of concept. But any questions so far? Does that all make sense up to this point? Okay. Yeah, go ahead.
I saw the KL divergence in some cases are using approximate. So it's is that the complexity of calculating it? It's high or
yeah. So there's a couple different cases, and we'll see. Yeah, maybe we should put a pin in that question. There's a couple different cases, but let me just give a real quick answer, but it'll come up again in what I have planned to talk about. So the KL divergence like I just mentioned, I mean, you can think of it across multiple applications. Anytime you have two distributions and you want to know something about how different they are, KL divergence is one way to measure that. But in terms of machine learning, like I just mentioned, we're typically we have parameters to some distribution. One of these distributions, we have parameters, sometimes maybe both, but let's just say one of these, the Q, we have parameters for. It's our model parameters. And we're trying to minimize something, a loss function. And you typically don't minimize KL divergence directly, but you have a loss function, like if I'll bring it back up again, the VAE, we had the elbow. And in the EM algorithm, we had this thing called the Q function, and I'll bring these back up again. And those are the things we actually minimize or maximize, depending on which way you flip it around. And what you can show is that they're actually, in the end, there's a KL divergence in there somehow playing a role. And the idea is, again, like you might have something very difficult to work with. And in the EM algorithm, it's a parameterized distribution, but I can't actually evaluate it. In Bayesian machine learning or statistics, I have a posterior distribution, and very often it has a very difficult denominator that has an integral over all the possible data I could ever see, which is impossible to, that denominator, what's called evidence, is impossible to compute. And so I can't work with this P directly and try to model it and optimize the parameters of that. So I work with an approximation to P called this little q distribution. And I make it something that maybe it's hard to work with, but it's at least tractable. I can approximate the P or whatever I'm trying to approximate, and show that what I'm really doing is minimizing the KL divergence between what I really want and the thing I'm using to approximate what I want. And like I said, for generative models, you can think of the P as the data distribution, the distribution my data really comes from. And of course, I think of the distribution of all cat images. There's no way I know that distribution like perfectly. I could perfectly sample from the distribution of all cat images. And so what I do is I have some type of model that's going to model that distribution. That's what I'm going to call Q. And then I'm going to, it could be a diffusion model, it could be a GAN, it could be a variational autoencoder, whatever it's going to be, or it could be just a Gaussian. The really bad model of images would be just a Gaussian distribution. And I want to just, try to approximate the data distribution by minimizing the scale divergence. And of course, because I can't compute the exact distribution of cat images, I can't actually compute the scale divergence. But what we do is we show if I have, I do this derivation, and I have a thing where I show that I optimize something that implicitly is actually minimizing this thing I want to minimize. So that's kind of the trick in the end. I'll bring all this up as more concretely here in a minute. Yeah, great question. Okay. So yeah, so let's, let me see. Oh yeah, this was the other, I'm actually going to leave off one of the properties I was going to explain. It's kind of esoteric, not really interesting, practically speaking. This was one of the other properties I was going to have as a property. I've already done it though, is number 3, is that the KL divergence decomposes as the cross entropy between your two distributions minus the entropy of the P distribution. That's the other property to mention here. Okay. If you go to Wikipedia, you can find there's like 4 or 5, probably more properties that KL divergence has that maybe are less useful, but somewhat interesting. But those are the ones I was going to highlight. Okay, and let's really dig into this property number 2 here. The positivity or non-negativity and equality only if you have really matched the P and Q distributions. And to get there, we first need a very important inequality that's a pretty critical development called Jensen's inequality. How many people have seen this before? Jensen's inequality. Okay, not so many. in fact, 0 people at least that admit they've seen that. Okay, and this Jensen guy is the same name as the Jensen-Shannon divergence and Jensen-Shannon. So Jensen, obviously, and Shannon we talked about last time is the Claude Shannon information theory guy. So Jensen's inequality, and this is like really old. I mean, 1906, because I just looked up it on Wikipedia this morning. Jensen proves this inequality, so it's a pretty old property, and really had related versions of it that were even back to the 1800s. So it's a pretty old inequality, but again, it's kind of like this key ingredient that makes a lot of machine learning work. And so it deals with the following. Let's say I have phi is a convex function. And I really just mean phi is just a real valued function. It's just real numbers to real numbers, okay? And convex, let's remember what it means to be convex. If I have x here, and I have some phi of x function here, what I mean is that if you give me 2 points, x0, x1, let me put those on the left, x0, x1, I can draw a line between them, the phi of x0 and the phi of x1. A line of the graph there basically, and any point in between x0 and x1, let's say x prime, then phi of x prime is going to be less than phi of x prime is going to be less than or equal to let's call this line AX. Let's see. So this line, I'll call AX plus B. Okay, so just the line that connects any 2 endpoints. This is the case for any 2 endpoints. Okay. Any questions there? Just I think everybody knows convex functions of the real line, but this is just a reminder. Then one other way to say this, equivalent to this definition of connecting the dots for convexity, is the following picture, which is what we're going to use to prove what we're going to call Jensen's inequality, is that the same any convex function here, phi of x, if I give you single point, let's call it x naught, this is again the x-axis, I can find a line, and again, I'll call this is a different line, but I'll just call it ax plus b again. Again, this is defined for all x, such that now the line is below phi of x, right? So I'll say phi of x is greater than or equal to ax plus b. This is for all x. And at least at the point x naught, it's exactly equal. The inequality becomes an equality, a x naught plus b. Okay, so that's another way of saying the same thing. This is equivalent. And if you haven't seen this before, this version of convexity, you can show it's the same as this version. Convex functions are always continuous, so I don't have to worry about gaps and things, but it doesn't have to be differential. I've drawn like a nice parabola or something, but it doesn't have to even have to be a differentiable function. It can have like corners in it. It could be like piecewise linear kind of thing, whatever it had. And this line doesn't have to be tangent. It can kind of meet over a stretch, like it could be equal for, like it's a piecewise linear function, for instance. You could take a line that is part of the piecewise linear segment, if you will. But the point is, I can always do this for any x naught. I can find a line such that the line is all the way is below phi of x for all x and touching at x naught. Okay. Strictly convex. This is convex, but strictly convex this would be greater than for all x except for only this point. Only x naught would there be equality. But for just convex, when you don't say strictly, it could be multiple x's where it meets the line. Okay, and we only need the convex. We don't need strictly convex for what we're going to do here. Okay, so yeah, and remember, just we're going on this little tangent, if you will, on Jensen's inequality. But I'll just remind everyone what we're trying to do is we're trying to prove this property of KL divergence up here, that it's strictly non-negative, or sorry, that's non-negative and equal when the P and Q distributions meet. Okay. Right. So if phi is a convex function, Jensen's inequality says the following. I'll say if phi is a convex function, then right. The expected, and I'm assuming that I have that random variable on x, and x is not necessarily the same as this real line here, but I have some random variable. If I take the expected value of phi of this random variable x, that is going to be greater than or equal to pulling the phi on the outside of the expectation. Okay, obviously these aren't equal in general, right? Because phi could be a nonlinear function. If it's a linear function, obviously phi would come out because we know expectation is linear. But for a nonlinear function, you can't just pull phi outside the expectation. But what we can show is if you have a convex function, if you pull the phi out, I can at least say it's going to be greater than or equal to the ends on the inside to be greater than or equal to pulling it out on the outside. Okay. So why is this true? So it's going to be really because of this picture down here. So the proof here is pretty quick when we see this. What we're going to do is in this picture, we're going to define x naught to be the expected value of x. Okay. And of course, I can do that. X naught is just any point in this picture here. This is true for any point. So I can say, and the expected value of a random variable is a number. So we just say x naught is equal to that number. Okay. And so then what I can show is the following sequence. The expected value of phi of x is, and I'm going to use this thing right here. So I can find a line ax plus b such that phi of x is greater than or equal to ax plus b for all x. This is after having defined what my x naught is, which I've defined here. Then I just know already that if that's true for all x, then it's true to take the expectation of both sides of this equation or inequality, right? I'm taking expected value of this side, expected value of that side. That's all I'm doing here. Okay. And now we can use the linearity of expected value. I can say that this, of course, equals pulling out the A, pulling out the B. Yeah. It looks like this, right? Okay, and now I'm going to use the fact that x naught was this e of x. Okay, so putting back in my x naught for e of x. And now I've got this, which I can say is equal to phi of x naught. And now I'm going to put it back, flip it back, make my x naught equal to e of x. This is phi e of x. Okay. And now I've got what I wanted. I've got e of phi of x is greater than or equal to phi of v of x in the end. Okay. So very useful tool when you're doing expected values of functions of random variables. If you have a convex function, you can pull it out if you're okay with inequality rather than an equality. Okay, and that's Jensen's inequality. Any questions about what we did just there? Okay, great. So now we're ready to prove property number 2 over here. Let me maybe come back over here to do it, since now that we have Jensen's inequality, what I'm going to do is say the KL divergence between from P to Q is just by definition the expected value or the P distribution of log, keep doing this, log P over Q. Okay. And now I want to use Jensen's inequality. I'm going to want a convex function inside here. Now log, remember, sorry, let's see, I want a right. Hang on. Yeah, right, exactly. So log is not convex, right? It looks like this, something like that, if I draw it poorly. But if I negate it, do negative log, I get right something like this. This is negative log. This is log. Okay. So if I just negate log, I should have gone below 0. Sorry, but you get the point. You flip it upside down, log, and you get a convex function. Okay. So what I'm going to do is I'm going to also remember if I take 1 over the thing inside the log, that's the same. I can pull the 1 over into a minus sign. So if I take P over Q and flip it to Q over P, then I can pull this negative out. So that's what I'm going to do to get a nice convex function inside my expectation. Is I'm just going to flip the ratio P over Q to Q over P. That's going to bring a negative 1 factor in there. Okay, so now negative log is my convex function, my phi over here in Jensen's inequality. And so now I know I can make that greater than or equal to pulling out the phi, which is negative log. Whoops, I was about to write phi again here. Pull negative log of my convex function outside of the expectation. I should put the p's here just to keep reminding us that we're taking an expected value for p. But now I've got q over p on the inside there. Okay. Any questions about the steps so far? That's the key step, is we prove Jensen's inequality for convex functions. I can do this, pull the negative log out. Okay. And now, I mean, again, this works for continuous or discrete random variables, but I'm going to write it in terms of continuous random variables. The expectation is an integral, but if it's discrete, you just do a sum. But let's write the expectation as integral of p of x times q of x over p of x dx. Things I need like that. Okay. And of course the p's cancel out here in the part here. So I've just got the integral of q of x. And of course, q of x is a probability density function, so it integrates to 1. So I've got minus log of 1. Log of 1 is just 0. Okay. So notice I've got the thing I wanted up here now. If I take the whole chain that we did here, the KL divergence is greater than or equal to 0. Okay. And if we ignore the almost everywhere for a moment and just think intuitively, let's just say P and Q are density functions that are equal everywhere. Of course, we know P over Q would be 1. And I'm taking log of 1, which is 0. Expected value of 0 is 0. So this is true if P and Q are the same distribution. Okay, so we've proven both these pieces. All right. And if you're familiar with the almost everywhere stuff, then you know that P and Q are equal almost everywhere. I'm integrating over P, measure P. And so things that are 0 almost everywhere are going to integrate to 0. So it does work with the almost everywhere caveat, if you will. Okay, any questions about this whole sequence of derivations? Yeah, so again, if you, I feel like if you really want strong understanding of modern machine learning and kind of all the things that are coming out like in the past even year or two, like with generative AI and everything, knowing this math is, I think, the foundational math underneath all of it. So if you have to rewatch one lecture for the semester or think or go deeper, like go study it more carefully, study this stuff, study the derivations of these things. And then the next thing we're going to do to actually show where the KL divergence comes up here in VAEs and EM algorithm and so forth. But yeah, this is kind of, I'm biased. Obviously, you could just learn how to do PyTorch and not know the math behind it. But if you really want to understand models today, I think this is the math to really know. Okay. Cool. Right. So now let's see. So now that we've got this important property, I said that's kind of the key property, the fact that it's always greater than or equal to 0, and it's equal to 0. You can minimize it if you make P and Q the same. Let's look at some of the things that KL divergence does just intuitively. And this is going to be more hand-wavy properties, if you will, of KL divergence. But you can try this yourself if you want to really go dive into understanding KL divergence. I will just kind of sketch what's going on, and you could actually set this up in code and try it yourself, and the equations and so forth. But I'll just explain it. Let's take the following very simple example, which you wouldn't do in practice, but again, it gives us intuition for what is actually going on with KL divergence. So again, like I said, very often what will happen is you have a P distribution, which is very hard to work with. You want to approximate it with a Q distribution, which is easy to work with. So let's take a very simple example of just a two-dimensional Gaussian distribution. So I have a normal distribution with a mean and any covariance you want, okay? And remember that if I look at like level sets of the density function, it's going to be centered at mu, that's going to be the peak. And then the covariance will give me kind of like elliptical level sets of this hill that kind of dies off, right? And that if I have an unconstrained covariance, right, if I get some correlation between the two dimensions, then I'll have some kind of diagonal elliptical covariance, right? And that has this kind of angle to it is because of the correlation between the X and Y components of my bivariate Gaussian. Now, let's say we're like doing machine learning in 1950 or something, maybe, where it's very expensive to model a 2x2 matrix. That means that's like too many parameters for you. Obviously, that's not a problem today, where we have millions of parameters in our models now, but it's instructive to what is going on here. So let's say we wanted to simplify this to, let's say this is our P, and our Q, we want, to do a normal distribution, again with some mean. We're okay to estimate the mean, but let's say we want to simplify our covariance down to just one number instead of 3, because you have to have 3 for symmetric covariance. We want to model it as just sigma squared times the identity. This kind of Gaussian will also be centered at mu if we can find the right mu, but it'll be isotropic, meaning the level sets will be nicely symmetric, circularly symmetric around mu, right? Just a hill that dies off in all directions with the same kind of shape. Okay, everybody okay with what we're doing here? So now let's see what would happen if I tried to use KL divergence. I've got one, let's say I know mu, so we'll fix mu is always the right answer. But let's say I've got one parameter I'm trying to find in my Q distribution, and I'm going to find it by minimizing the KL divergence between P and Q. What's going to happen? So let's say, let me do it down here. So I'm going to redraw my picture of P. And I'm going to say, let's minimize over the Q distribution, the KL divergence of P to Q, like so. Okay, what ends up happening is that you have an isotropic distribution. I really need two colors, but I don't have them really. So you have an isotropic distribution that goes very wide. Okay, it tries to cover everywhere that the hill has any kind of height in the P distribution. And I'll come back to why this is the case in just a minute, but let me just draw the cases, because what I'm going to do is say, well, let's try the other way around, because remember, KL divergence is not symmetric. What if I try to flip Q and P and say, minimize the Q distribution again is one parameter such that I best shrink it as much as I can to KL divergence between Q and P in the opposite order. Now, what's going to happen is I'm going to find a Q distribution, which is a very sharp peak that tries to cover up everything that's in the peak. So it's really more concentrated on the mode or the peak of the Gaussian, whereas here, what we're trying to do is make sure we cover all of the density that could possibly be popping up in our P distribution. Okay. Now, why is this the case? So if just again, kind of a hand wavy, but if you look at the KL divergence from P Q, just bring up this definition again. We have the expected value under the P distribution of log P over Q. And now let's take a look at what's expensive here. What would cause me to have a really bad KL divergence between P and Q? It's the Q in the denominator. So if Q goes to 0, right, then and P does not go to 0, I should specify, then that's going to cost me a lot. Oh, sorry about the camera. That's going to cost me a lot in this KL divergence. So in this picture, PQ, right, that's in the same order out here. Q in the denominator means that anytime Q goes to 0, this density goes to 0, it better be the case that P's also gone to 0. Okay, so if I did something like this, Q would go to 0, but P is non-zero. So I'd be averaging something, and sorry, it's not exactly 0, we know with Gaussians, but close to 0, log 1 over Q, where Q is close to 0, is some very large number, right? And so this would be very bad for KL divergence here. Vice versa, if I flip the order, now P, just flip P's and Q's, I'm going to be integrating over the Q distribution, and P is going to be in the denominator. Anytime it becomes close to 0 and Q's not 0, I'm going to be in trouble. Okay, we can pay a big KL divergence penalty, if you will. And so I want to make sure that anytime P goes to 0, that Q has sufficiently died off as well. Or I should say close, as Q's close to, or sorry, P's close to zero out here. I want to make sure that Q dies off at least as fast as P, if not faster. Okay. Another way of saying it, kind of counterpositive or whatever, if you will, it's okay for the distribution that is second to have positive mass, where the first distribution, the Q distribution in this case, is close to zero. That's okay, because that'll be integrating over Q will be basically add zero to the KL divergence. Okay, so I really, if I'm trying to, again, do this case, in this case, I'm going to try to make sure I cover everything in this order around to where I can move the thing on the left. I'm going to try to find the peak. I'm going to look for the peak here. Another way of illustrating this, which is a similar, you can do the mental logic yourself, but I'll just kind of draw the picture, is let's say, and this does become more relevant to modern day machine learning. Let's say I have a distribution where my P distribution that's hard to model has, you know, like multiple peaks, right? So it's you know, like two hills here. Okay, same picture, and let's say they're not Gaussians, they're kind of wiggly squiggly whatevers, right? And now I want to model it with a simple distribution like a Gaussian. The question would be, do you want to use your single Gaussian Q to do something that looks like this, just covers the whole picture, right? That would be what would happen if you minimize KL divergence in this case. Or do you want it to find one of these peaks really well and completely ignore the other peak? And here you get stuck in local minima, right? Because I might latch onto this one or I might latch onto that one. I can't really be sure, frankly. And in that case, if you did want to do that, let's say you've got lots of peaks popping up, you want to just make sure that you capture one very good, like local peak, then you would do your KL divergence the flip way around. Okay, so this is kind of the main intuition, kind of as in picture form, I think, of what it means to minimize KL divergence and what the asymmetry of the KL divergence really is doing. Okay. Right, any questions up to this point? I think I'm actually running right perfect timing, which is a first for the entire semester. And I'm going to get in everything I wanted to get in. Okay, no other questions yet? Okay, so now that we've done KL divergence and this very key property and kind of motivated why we care about KL divergence, let's look at going back, and this will be a little bit repetitive what we did, but I mean, now that we have this understanding of KL divergence, it'll hopefully make really nice connections to what we've done in class in a few different places. Okay. All right. Okay, so again, I can think of machine learning as in various ways trying to model some probability distribution, P of X. Really, I should say most relevant here, I'm not going to talk about classifiers, although we could. We didn't spend too much time on classifiers, more on generative models. And generative models, let me say very, very specifically, generative models, the goal is to model P of X, where P of X is your data distribution. You don't know it, but you want to model and be able to sample from P of X if you could, but we can't. So like I said, we're going to get some other distribution we can sample from that is as good as we can do when we don't know the true P of X. Okay, and so the following equation I'm going to do, I'm going to write P of X in a particular form that again is going to be very general using KL divergence. and kind of across the board generative models that talk about probability distributions at least, really kind of fall into this again overarching picture. I would argue. So what we're going to do is we're going to take log of p of x, because that's usually a thing we do. And logs have nice properties we like. And we're going to write that as an integral over q of z. Now q is just some distribution I'm introducing. It doesn't, for the time being, matter. Exactly what it is, just that it's a distribution on z, and we integrate this over z, and this is equal, right? Because log p of x is just a constant in z, and so this is the same thing as saying the expected value in the z variable of log p of x. P of x doesn't depend on z. This is just a constant. So I'm taking the expected value of a constant, which is just that constant, which is log p of x. Okay. So I'm just introducing this z variable and running with that. Now z, let me connect it to things we've talked about. Z, x is our data. We observe x's. We see x's coming at us, right? But z is a latent variable, a hidden variable. And this can mean a lot of different things depending on what exactly we're doing. We've done a lot of stuff with autoencoders, variational autoencoders, for example. So Z would be the latent space that we encode in and decode out of. So in the variational autoencoder, that's what Z was. Same thing, if you were talking about GANs, you would have Z as a latent space, a low dimensional latent space that you generate data from. In the Gaussian mixture model case, let me just do a little sidebar here. So I'll just kind of, this is like old school machine learning. Before everybody was doing deep learning, there was clustering on Gaussian mixture models. I'll just do the 1D case. We would have like, several different Gaussians, and you have data, and you would try to find the parameters for the Gaussians, where the means and variances, and this could be multivariate, is more interesting, obviously. And then you would assign data to a particular cluster 1, 2, or 3, right? And the latent variable that you don't observe is which of these 3 clusters. It's the label, it's the category, that which, if I give you a data point of X, the Z associated with that data point is which cluster does it belong to. And again, Aman kind of touched on this when he talked about the Gaussian mixture models. The latent variable there is discrete. It's a category, like 1, 2, 3. Okay, so Z's can be, I'm writing as an integral, but it could be also discrete. It can be a summation, the expected value I just drew there. So yeah, so Gaussian mixture models fall into this category, variational autoencoders, diffusion models, let's talk about those. The latent space is the same as the X image space that we're doing images. Because remember, we kind of add noise from our original X data until it becomes almost pure noise, right? And that's the Z variable. That's kind of the latent space you're working in, is the same size as the images. And so that's kind of what's going on in the diffusion models. So yeah, so this is, again, very general. For generative models, we have a picture that looks like this. Okay. So yeah, but we can ignore all that and just think of 2 distributions, P of X, Q of Z. This algebra we're going to do is just going to work out for any 2 distributions. But that's what we're really doing is generative models here, really. So yeah, so this integral, I'm going to rewrite the log term here. By multiplying what will seem like a silly thing to do, but I'm going to take P of Z given X times Q of Z, multiply it in the numerator here and in the denominator. So I'm really just multiplying by 1. That's all same thing as just P of X, of course, inside my log. So that step is to get some more terms in here that we're going to play with. And then I can write this as an integral over QZ. I'm now going to take these two terms and combine them. Just remember your multiplication rule from probability is that the x distribution times the z given x distribution gives you the joint distribution p of x and z. Okay, so I'm going to use that property to say that this is log p of x and z over qz by pz. And now the thing that's left, I'm using this QZ here. I'm going to use this top QZ and this P of Z given X is what's left. And I'm just put a negative sign in here and flip the ratio. So this becomes minus integral of log P of Z given X divided by Q of Z. Okay, and these are actually both look like KL divergences. Oops, I left out a QZ. Integral Q Z. Okay. Actually don't do the negative. Anyway, it doesn't matter. What I'm going to call this term, I'm going to call L, with a little script here, Q. And this term, I really could have kept those flipped actually, but now that I think about it. If I flip those back over, I won't do it, but if I flip that back over, it's the KL divergence with Q being the first one, P of Z given X being the second one. Right, so this is the KL divergence of Q. Let's see, yeah, Q's the first one in the sequence. Got to always get that right. And this is P of, I'm just going to write as a subscript Z given X distribution. And they're both distributions from Z because the X is a constant. It's like data I've observed, and Z is random variable. Q's random variable of Z. So these are both Z random variables. Okay. So this is just a definition of this term is what I'm calling script L, okay? And now it turns out that all the ways we saw of doing these generative models can be written this way, whether I'm doing the Gaussian mixture model, whereas these are the labels, and again, I have to do sums instead of integrals, or I'm doing, I'll talk about VAE, where Q of Z is really going to be Q of Z given X, and it's the encoder of my variational autoencoder. If you remember, we had a variational autoencoder with like a Q of Z given X, and it was the thing, camera just randomly switched on me. It was the thing that was our encoder. Okay, right, and so how are these connected? I spoke too soon about being on time because now I'm realizing 8 minutes is going to squeeze this last bit a little bit tight, but I think we can do it. Okay, so the expectation maximization algorithm, EM algorithm, was the thing that Aman talked about with mixture models, but it's very, very general to solve problems with a latent hidden variable, like the labels of the clusters is a hidden variable. The thing is that if you knew the labels of the data point, the trick is if I know the labels of the data point, it's easy to estimate the Gaussians. I just take all the ones that are labeled 1 and I estimate a Gaussian for all those, and that's my Gaussian number 1. All the label 2 guys, I get estimated Gaussian for them and so forth. But if you don't know the labels, and I just say, here's a bunch of data that could have come from any of these 3 Gaussians or however many I have, it's very difficult to do that from the outset. And so the EM algorithm and thinking of Z as a latent variable and a hidden variable is a very elegant way to do this. And so in the EM algorithm, our goal was to maximize parameters of our probability distribution that are usual things, and law of likelihood. And without the Z's in there, I just say, here's a bunch of data, which I don't know which galaxies they go to. This is very hard to write down. It's intractable. Okay, but what we do is we make something that is tractable. We make a Q of Z, which is equal to the posterior probability of our label. Z's are label for observed data point X. And we have a parameter vector, which is like the means of the Gaussians, the variances of the Gaussians, and also kind of like the frequencies of the Z's, like how often do I get label 1, 2, or 3, or whichever. I take it iteratively, I update this. And so I say theta old is from the previous iteration. I use that one to get a new estimate for theta. I'm going to call theta new in the next iteration. And my L function here, if I call Q this thing, my L function here is what we in the EM algorithm call the capital Q function, which is the function of theta. If you know I should write it maybe this way, theta given the previous theta old. And I'm going to maximize the Q function, the M, the expectation maximization. The expectation is doing all this trick. The maximization is you then get it down to a form you can actually work with, the Q function. I can maximize this with the function as a function of theta, if I know my previous iterations theta old. And the picture of what's going on is the following. I know, if I come back over here, KL divergence, that very important property, this term is greater than or equal to 0. And what that lets me say is that I want to always maximize log P of X, that with respect to theta, that's my goal. It's really hard to do. I'm instead going to maximize this, and I'm guaranteed, because this is a positive value, that if you maximize this, this is a lower bound for this. I'll always also increase this. I won't necessarily maximize it in one step, but I'll always increase it. And I'll keep increasing if I do this iteratively until I can't go any further, and then I'll be at the maximum of this thing I want. So the picture I had in mind is the following. So this is my log P of X with respect to theta. I'm maximizing over theta. I've observed X, it's constant. I'm trying to maximize over theta. I'm trying to find the theta that gets me to the top of log P of X. And I can't evaluate log P of X easily. And so I compute this Q function. I'm going to say my Q function looks like this. It's again a function of theta. If I have a current estimate theta old. And at my theta old, they're equal. So at theta old, if theta equals theta old, I'm at this kind of point where they touch, because the KL divergence will be 0. Okay, and that term, that bound, will become an equality. But I want to change theta to get a better answer. So I maximize Q theta, I go up. I'm guaranteed that this goes up to still stay below the thing I'm trying to maximize. That's why the lower bound is important. And if I go up, because these touch, this has to be a better answer for the thing I'm trying to maximize also. And then I repeat that process over and over again. So then I'll refit my Q function. This will become my theta old. I'll refit it as another kind of thing that touches, but is still bounded below. And I'll repeat that process. And you keep going until your Q function has the same maximum as your log P that you want to maximize. Okay, and that's how the EM algorithm really works. Because of this KL divergence property, the bound, this Q function is a lower bound on the thing you actually want to maximize. Okay, really quickly, this same picture on the far left board is what we're doing when we do variational approximations, like the variational autoencoder, and also the diffusion models. They both use a variational approximation to the thing we'd actually like to do, but is very difficult. And I'm going to do this really quickly because I only got 2 minutes. So variational methods. Variational approximation. What we're doing there is that we have some latent space. And in our case, the latent space, like we said, is like in autoencoding or diffusion models, or generative models more broadly. I'm trying to say now what Q is approximating a different thing. It's a subtle difference, but it's approximating the posterior of Z given X. So I'm trying to make this approximately equal to what's the latent variable for my data point X. And we think of encoding autoencoders. This is like, give me an X, encode it into a latent variable Z. This is like an encoder. So our encoders and autoencoders, variational autoencoders, look like this Q of Z given X. Okay, and if you go back to the variational autoencoder slides or the lecture, and look at the derivation of the equation for that, you'll see this same notation L of Q. I think I say L of Q theta phi. There's some the parameters theta phi there. This is what we were calling the elbow, the evidence lower bound. And that's the thing you actually optimize in variational autoencoders and really all variational methods is this thing called the elbow. Okay, but the same argument on the far left board is valid, that if you optimize the elbow, actually it's a slightly different argument. So see if you can follow this logic in the last 10 seconds I have. If you optimize the elbow by getting you're fitting the Q as best you can, this is a constant. This is just, if you give me a data point, P of X is just its probability on the data distribution. I don't know it, but it's a constant. What I really want to do is I want to maximize this, minimize this. I want my Q of Z given X, because remember, the picture there is Q of Z given X is an approximation to the posterior P of Z given X. Again, I don't really know how to do P of Z given X exactly. It's kind of like the best autoencoder or true autoencoder I would get if I knew the data distribution. So I approximate Q of Z given X, and I want to minimize this. I want to drive this to 0. So it's a little bit different goal than the EM algorithm. In the EM algorithm, this is kind of fixed. But I want to drive Q is close to this. So I want to drive it down to 0. I can do that by minimizing the elbow. As this goes down, because this stays constant, as this goes down, this has to go up to stay constant. So I can't tackle the KL divergence directly because I can't compute it. So I tackle the elbow, I bring it down, and that implicitly improves my, sorry, I'm going the wrong way here. I want to KL divergence down, so I maximize the elbow. Right, yeah, other way around. So that's I increase the elbow, I drive the KL divergence down to 0, or as close to 0 as I can get resplit. Okay, that's the theory of everything, since I see it. Thanks everybody for a great semester, and I'm looking forward to your talks on Tuesday. Thanks. I'm happy to stick in and answer questions if anybody has them.
Is the homework extended to today or is Wednesday?
It was Wednesday. So today's like 1 day late.
I thought it's Thursday.
No, it's a. Yeah, this is Wednesday.
One more question, Professor. So like we do the evaluations, there's extra points.